So far we have talked about the various over voltages that are likely in a system. Now let us go on to the next step, that is insulation coordination. Now if you remember, I have talked about insulation coordination and I have said that there are two ways to go about insulation coordination. One is to limit the over voltage and the second is to provide insulation. So firstly we are going to talk about limiting the over voltage in the system. So insulation coordination involves the correlation of the insulation of the electrical equipment with the characteristics of protective devices such that the insulation is protected from excessive over voltages. What are these characteristics that I'm talking about? I'll come to later. But right now let us consider this phrase that the insulation is to be protected from excessive over voltages. Now, you now know what is the kind of over voltage that you expect would appear at a particular point in the network. So any equipment that is put at that point must have enough insulation so that it can withstand that stress. Whatever over voltage we expect at a particular point in the network has to be withstood by the insulation that you provide to the device at that point. So that means the insulation level is determined by the over voltage level. That is a way of doing things, and theoretically it is a valid way of doing things. But if you do that, then the kind of insulation levels that you would have to work with would be enormous. That means you will have to provide a very large quantity of insulation, and that will either make your equipment very bulky and it will also become very expensive. Of course, you can go for materials with higher dielectric strength, but definitely it means that it is going to increase your expenses. So therefore, in practical terms, excessive insulation is not an option. And as I keep telling you, that insulation is the part of the equipment which you would like to get rid of. You want to minimize it. You don't want more of it. So therefore, you want to use less insulation. If you want to use less insulation and not lose out on functionality, then there must be a way of preventing that magnitude, that very high magnitudes of over voltages from appearing across the insulation system. And therefore, we have to look at some protective measures. So therefore, for higher insulation levels especially, this is true, you do not want to go for excessive insulation, and therefore the first step that you have to do is you have to devise protective devices which will be installed at sensitive points in your network. You know that there is a particular over voltage level which is likely at a particular point. At that point, you will incorporate a protective device. And the function of the protective device is to make sure that the over voltage magnitude that appears across your equipment is diminished. So only up to a certain level, over voltages will appear across the insulation. Over voltages in excess of that level will be prevented by some means from appearing across the insulation. So you're actually talking about protection. Before you think of strengthening the insulation so that it can withstand the over voltage, you try to prevent certain over voltages from at all appearing across the insulation. The actual relationship between the insulation levels and protective levels is a question of economics. So there is an insulation level. What is the insulation level? Insulation level is what determines the insulation, the design of the insulation of your equipment. The equipment is designed to withstand stresses up to the insulation level, whereas the protection level or the protective level is the level of the over voltage against which the insulation is protected. Let us see, and so how do you choose this protection level and insulation level? That is a matter of, that's kind of engineering judgment. That means how much are you going to save on insulation by providing protection? How much protection is cost worthy? So those things are there. Let us just look at the concept of protection and insulation levels. So let's say you have a protecting equipment which will be protected, and there is a protecting device. So at any point in the line, you are aware of the level of overvoltage that you expect. You do not design the equipment with sufficient insulation to be able to withstand that overvoltage. Instead, at that point, across the insulation to be protected, you plug a protective device. And this protective device will take care of a certain level of the overvoltage. So protect the system insulation using devices that restrain the voltage across the equipment insulation down to acceptable levels. It reduces, the protection system will reduce the magnitude of the overvoltage. It will also control the amplitude and stiffness of the surges, so it will kind of modulate the wave shape and the frequency of very high overvoltages. Now, if we have been talking about breakdown characteristics, the most important characteristic at the moment that we are interested in, that's the simplest thing that we always have to look for, the first step, is the disruptive discharge. So at what voltage does the dielectric break down and loses its dielectric property? That is the main characteristic of interest. And now we have talked about so many different processes. We are aware that there are various processes by which breakdown can occur, and the processes are very different depending upon whether it's a gas, a liquid, a vacuum, and most importantly, in an insulation system, you have composite insulators. So it depends upon the constituents of a composite material. Then in addition to a composite material, you can have different kinds of composite or homogeneous materials in proximity. And as we have seen, that proximity will change the nature in which breakdown occurs. So it is very difficult for us to predict for an insulation system how breakdown will occur. And therefore, we have to accept that the physical processes which leads to breakdown, we understand these processes somewhat, not fully, but most importantly, these are random processes. So therefore, breakdown is a stochastic process. It's not a deterministic process. You cannot predict at what time, at what level breakdown will happen. And therefore, we first will talk about a breakdown characteristic. We'll talk about probability. We will talk about the probability of withstanding a certain voltage. Let us assume that I apply a voltage capital V across an insulation system. I can only talk about the probability of such breakdown. I can only talk about the probability of failure at voltage V or the probability of withstand at voltage V. I cannot say with certainty that when V is applied, breakdown will definitely occur or breakdown will not definitely occur. Most of the time, I cannot say. And why cannot I say? This probability, I will talk about that a little more, but right now there is only one aspect that I want to talk about, stress upon, and that is the probability whether failure will occur when a voltage V is applied across the system depends, of course, on the stress across the system. So when you apply voltage V, what is the electrical stress across the system? If this electrical stress exceeds the breakdown strength of the material, breakdown will occur. If it does not exceed, breakdown will not occur. However, remember that breakdown does not necessarily occur as soon as the breakdown strength is exceeded. And sometimes breakdown can occur even when you are at levels below the breakdown strength. So it is a function of S. It is not a deterministic function of S, but it is a probabilistic function of S. Additionally, it is also a function of time t. So the same stress, if you apply it several times in succession, breakdown may or may not occur. So that is why we are talking about the probability of breakdown. We are not saying, okay, breakdown will happen or breakdown will not happen. That is the stress part. But in addition to that, the same stress, the same voltage, if you apply for a certain length of time, breakdown may or may not occur. So for example, if you apply a very high voltage, and you apply it for a very short duration. Let's say you applied it for 10 seconds. Breakdown happens. Now let's say you halve that. You halve that and you keep the voltage applied. The breakdown may happen even at that lower voltage, but it will take a much longer time. So therefore, the stress that you apply and what is the time duration for which you apply that stress, both of these things will determine whether breakdown will happen or not when you apply a voltage V across an insulation system. However, both the time as well as the stress is a random the failure at the stress or at this particular time is of random nature. So one time you apply a voltage V, breakdown occurs. Next time breakdown does not occur. So it's a probabilistic event. And the same voltage V, if you apply for T seconds the first time, breakdown may happen. Next time, breakdown may not happen at T seconds, breakdown may happen at a much longer period. So the dependence on time as well as stress are probabilistic in nature, and we will discuss later how we obtain these probabilities. Right now, I'm not going to talk about the probability part, but what I'm going to stress on is that probabilistically, the probabilistic nature is there, but apart from the probabilistic nature, the breakdown or the disruption, the disruptive discharge is a function of the stress on the material as well as the time for which it is applied. Whenever we talk about the probability, we also need to talk about the probability of withstance. So probability of failure at voltage V has a corresponding probability of withstand. And the probability of withstand Q is of course obtained from 1 minus P. So either it has to fail or it will not fail. These are the two events, so they have to add up to probability unity. So if you know the probability of failure at a certain voltage, you also know the probability of withstand at that particular voltage. So therefore, this is what we are talking about. We are talking about a volt time characteristics. So let's say A is one such characteristic. What is it a characteristic of? I will come to later. Some insulation. So as you can see, it has a slowly diminishing curve. It's a slowly diminishing curve, which means when you're applying very high voltages, the time to failure is small, and when you apply low voltages, the time to failure is not zero. The time to failure is not infinity. It's not that failure will not happen. Failure will happen, but it will only take longer times. So this is the kind of volt time characteristics you have. So it is not enough to know the breakdown strength. It is not also enough to have the probability distribution curve or deal with the breakdown strength in a probabilistic manner. We also need to incorporate time into the picture. We need to know what times will be required for breakdown to happen at that particular voltages. Now coming to the protective margin. So for every equipment insulation, you have to have a volt time characteristic. Now here we have two volt time characteristics. A is the volt time characteristic of the device, the insulation of the device which is being protected. So if you go back to the previous slide, this equipment, the insulation to be protected, this particular insulation has this particular volt time characteristic. Now, when you choose a protecting device, you have to make sure, B is the volt time characteristic of the device that is being protected. So, this insulation which is protected has the volt time characteristics given by B. And when you choose the protecting device, you have to have a volt time characteristic which is somewhat similar to A. So as you can see, the nature of both curves are similar. They go from higher levels to lower levels. A is the protecting device and B is the device to be protected. The difference between the two, which is again a function of time, is called the safety margin. What it means is that if you apply a voltage V across the insulation, both the insulation, they are, as you see, they are in parallel. So let us assume a voltage V appears on the line. When a voltage V appears on the line, and let's say it is higher than both these values. So let's say it's something like this. that is the case, then as you can see, this voltage will appear across the protecting device B as well as the protecting device A and the protected device B. But because A has a lower volt time characteristic, it will break down at a smaller voltage. So even before this high voltage can appear across B, A will have broken down, and we must make sure that there is a path which diverts or which allows the charge to flow through A. And therefore, B will not break down because A breaks down before B does. So if we go back to the previous slide, what this means is, I apply a particular voltage V here, and this is programmed to break down at a voltage VA, and this is programmed to break down at a voltage VB. And VB is a higher voltage. VB is a lower voltage. So, well before this insulation can break down, this is more vulnerable and this protective device breaks down and the voltage or the charge finds a path, a short circuit path to ground through the protective device. Therefore, the higher voltage which the insulation is able to withstand never appears across it. So that is the point of a protective device. The protecting device must have a volt time characteristics which is much lower over all times, much lower than the volt time characteristic of the device to be protected. And this difference at all times between the two volt time characteristics is called the safety margin. What safety margin you will use depends upon the particular application. We can also talk of something called the protecting ratio. The protecting ratio is the ratio of the maximum voltage that is permitted and the maximum surge voltage the equipment can withstand. So it is not necessary that if you design the protecting device to break down at VA, you will definitely provide insulation level only up to VA or low. You will go to a higher voltage because you want some protection, that if for example your protecting device fails, or for example for whatever something goes wrong, there is some safety. So it's not like voltages higher than VA will never appear across the equipment. It might, but the frequencies of such over voltages will be decreased. So this is what I meant here. As I said, the protective device controls the amplitude and stiffness of surges, which we understand the magnitude is reduced. So instead of having, even though you have an over voltage VO, which is greater than VA, VB both, you do not allow VB or V0 to appear across the insulation. You allow only VA to appear across the insulation, because when you have voltage VA, the protective device breaks down and no further voltage will come across your insulation. And then reduce the frequency of overvoltages in the system. So it is still possible that at VA, remember it's a probabilistic event, and then the protective device may also malfunction. So yes, even after you have provided the protecting device, it is possible that voltages greater than VA might appear across your insulation. But the frequency of such overvoltages, the probability of such overvoltages happening will be reduced. And therefore, we don't work with the insulation levels exactly equal to VA. We leave a safety margin so that even if voltages greater than VA appear across the system, it will still be able to withstand, because not until you reach VB, this volt time characteristics, will your insulation break down. And so this is the safety margin and this is the protection ratio. The protection ratio is the maximum voltage so if you consider a particular time, so at a particular time, what you have is, this is the maximum surge voltage, maximum voltage that will be permitted. And this voltage, the higher intersection point, will give the maximum voltage that the equipment can withstand. So the maximum voltage that the equipment can withstand is greater than the maximum voltage that will be permitted. And the ratio between these two voltages is the protection ratio, and the difference between these two at all points as a function of time is called the safety margin. So this is how we set about deciding the protection levels and the insulation levels. So an example of a protection device is surge diverter. The surge diverter, ideally speaking, should act as a perfect insulator. That means it has an infinite impedance and there is no leakage current flow as long as there is no over voltage. So let us continue to think about this as a surge diverter. And what does the surge diverter do? As long as there is no over voltage in the system, the line is functioning properly. We do not want the system to even see this. It serves no purpose. So if I do not want the system to see this, what should it do? It should act as a perfect insulator. It should have an infinite impedance and there should be no leakage current. But as soon as there is an over voltage, I want this surge diverter to swing into action. And not only that, I want it to have zero impedance. So I want it to go from infinite impedance instantaneously to zero impedance. What happens when this has zero impedance? It provides a perfect short circuit to earth, and the surge is therefore bypassed to earth and nothing. So as soon as over voltage occurs, the surge finds a path through the surge diverter to the ground and no part of the over voltage appears across the insulation system. This is what I ideally want. Again, as soon as the over voltage is cleared, let's say it's a temporary fault, transient fault. So there is a transient over voltage. So it has to go to zero impedance. As soon as the over voltage is cleared, I want the diver to regain its infinite impedance. So of course, this is not really practicable, but we approach approximations thereof. So the practical diverters generally consist of one or more air gaps which are connected in series. So we will discuss air gaps, breakdown of air gaps later, but you can imagine you can have the air gaps in such a way that the air gaps are set to break down at a particular voltage, at a particular stress. So you manage the gap distance and the cleanliness and everything, enclose it in a tank. Most of the time, that's what we will do. We will not leave it exposed to air so that we have better control. So these air gaps will break down. So as long as the air gaps are intact, they are like open switches and nothing happens, nothing passes through. At the moment of breakdown, it forms a perfect conducting path to ground. We should have these air gaps which are used in practical diverters, and we have several of them in series so that as soon as a particular voltage is reached, they will break down in succession. But before that, there is a very low probability of breakdown happening as long as there is no over voltage. We will talk about air gaps later when we talk about measuring equipment, so that part will become clearer. Of course, when we are talking about practical diverters, we need equipment, we need a material which has a fast arc quenching capacity. So when this arc is drawn, it provides a short circuit. Now, as soon as the over voltage is cleared, I do not want that short circuit to persist. So that short circuit has to be cleared very quickly, and for that I need a medium which has a fast arc quenching capacity. We might also add nonlinear resistors in parallel to aid this process. Also, whenever you have this short circuit, there is a arcing, there is a lot of energy which is going to be dissipated. And therefore, our surge diverters should be capable of dissipating this energy without damaging the device. Some examples of such protective devices are rod gap type devices, expulsion type arresters, valve type lightning arresters, but I'm not going to talk about these various surge diverters in this course. Here you see just an example of the kind of functionality we just talked about. So this is your surge voltage. This surge voltage would have appeared across your insulation. So let's say you have an insulation, and across this insulation you have, as you see here, you have silicon carbide surge diverter, or you have metal oxide surge diverters. These are commonly used surge diverters. These Diverters are placed in parallel to the equipment to be protected. Now, if that protecting device was not there, if the surge diverter was not there, this is the surge that you would see across your insulation, and your insulation would have had to be able to cope or withstand this surge. But when you have the surge diverter, what happens is as soon as the surge voltage reaches this value, the surge diverter, so up to this point where you have normal voltages, the surge diverter is kind of opaque, does not is opaque to the system. It does not contribute anything. And as soon as this overvoltage exceeds this given value, it breaks down. The surge diverter breaks down, and the surge diverter needs to hold, so it starts conducting electric current at a certain overvoltage, and it needs to hold the voltage with little change during the duration of the overvoltage. So the potential difference at across the protecting device should remain at a fixed point. It should not go to zero. It should remain at that normal voltage or somewhere close to that normal voltage during the entire duration of the overvoltage. And after the overvoltage is over, it should cease conduction at very nearly the same voltage at which the conduction started. So typically it should have been here, but that may not be possible, but at least it should not go down to very low levels. So the voltage drop should be held constant during its operation, and then it should regain its original insulating property. This is how a surge diverter typically should work.